Hi, my name is Joe Fieresi, and today I'll be presenting my ICLR paper titled ALBAR, Adversarial Learning Approach to Mitigate Biases in Action Recognition. The goal of video action recognition is to classify actions using mainly action or motion-related information. However, models will often exhibit some form of bias. This can broadly be categorized into two main forms. First being background bias, where you use the background to help decide the action, maybe looking at the ocean to decide surfing, or foreground bias, where you can help decide the action by looking at the foreground, maybe like a sporting jersey. This can be especially harmful if this foreground bias comes from demographic information, such as skin color or gender, and neither of these are solved problems. We can look at some examples of background bias using UCF 101. In this video, we see a man on a tennis court swinging a tennis racket, but if we replace the tennis court with an image of a horse, our baseline model will predict horse riding because it's not really using the motion, it's just using the presence of a horse. See something similar here with the golf swing. He's swinging a golf club, there's wide open greens, but if we replace the background with this generated office that has some random shapes, our baseline will predict hula hoop. We see a similar phenomenon here, but with foreground bias. If you look at the single frame here, it's pretty easy to predict passing American football just due to a sporting jersey. However, once you add motion to the video, you clearly see that he's doing an archery action. But most models will just see the jersey and predict the passing, not the archery action. We see something similar here where this guy is performing an air guitar action. So his motion is still guitar, but because there is no guitar object present, a model oftentimes will not predict it. Here we see the same thing, but with this playing violin action, except his hair sort of looks like spaghetti, so models will often predict eating spaghetti. The main intuition of our work is that these biases are due to static spatial information, so any information contributing to this bias can be found within a single frame. So as such, we propose this adversarial learning approach to mitigate these biases, where our adversary is actually the same network predicting actions with a clip with no motion. So in practice, this is just the cross entropy of the motion clip minus the cross entropy of the static clip. However, we find that this is unstable. It doesn't really work right out of the box, so we propose two supplementary objectives to help stabilize training, namely a static entropy maximization loss and a gradient penalty loss, which I'll explain shortly. Overall, though, we learn these high-quality temporal motion features by directly penalizing spatial information usage. So let's look at our framework diagram. First, if we could start with this clip with motion on the left and sample a single frame to build our static clip on the right. Both of these are passed through the same encoder to build our class-wise predictions. Then we can compute the cross entropy with respect to both, and to build our adversarial objective, we subtract the cross entropy with respect to the static clip. However, we find that in order to maximize this loss, the model will often flip the class prediction with high confidence. So to mitigate this, we propose to maximize the entropy with respect to the static clip, which is similar to matching it to a uniform distribution. We want low confidence given a static clip. However, this training is still pretty unstable, so empirically we find that it's useful to directly minimize this gradient norm with respect to the static clip. So overall, our training objective just takes in two input clips, one with motion, one without. We only have one model and no separate bias labels or predictor networks. Here are all of our equations. Please feel free to check out our paper for more detail. To evaluate our framework, we can start with a standard action recognition benchmark like HNB 51. We can look at background bias by replacing the background and trying to predict the action. Here we still want to be correct because all the motion exists, but we can evaluate foreground bias by sampling a single frame from this video. Here we want to be incorrect because if we get it correct, then we're using that foreground information to help classify the action. We can evaluate both foreground and background bias by taking a random scuba video, adding a different scuba foreground, and getting a single video where we want to predict wave but not golf swing. Looking at the HNB 51 protocol, we see that our baseline gets around 74%, but as soon as we replace the backgrounds, we see an over 30% reduction in performance, but without motion, we're still able to predict 20% of the videos correctly. Different works handle this trade-off to different degrees. Notably, the still mix work handles both background and foreground bias, but because we directly penalize spatial information usage, we get very strong performance on this foreground debiasing protocol, leading to very high combined debiasing scores. Our approach also scales to the much larger Kinetics 400 dataset. The existing UCF 101 protocol used bounding boxes to separate the foreground and the background. However, we update this to use segmentation masks, and as a result, we get state-of-the-art performance. Notably, our work doesn't just overfit to this action recognition task. We find that this debiasing actually results in improved performance on downstream anomaly detection and temporal action localization tasks. Here are the citations. Thank you all for listening. Please feel free to check out our paper for more details.